Welcome to this lecture on Bayesian Inference. I'm Ayush Pandey. I'm from Control and Dynamical Systems at California Institute of Technology. Before jumping into Bayesian Inference, let's quickly review the system identification problem. So for any system, whether it be bacterial cells, viruses, self-driving cars, or robots, we usually create mathematical models to predict the response of that system under input conditions, or to analyze the properties of that system. If the mathematical model is known, this can be very fast because you can just simulate that model. However, it is not straightforward to find out that mathematical model or to validate that model for the given reality of the system. So we use the experimental data to train that mathematical model, and this process can be very slow because it might require computationally inefficient processes or millions of simulations. So let's look at what are the different kinds of system identification methods possible. The first one here is the optimization method. So for an optimization method, what you usually have is a first principles model. By first principles, I mean a mathematical description of the physical processes as a nonlinear function f here, which is a function of the parameters and the inputs, and these parameters are usually physical parameters of the system, which may be helpful in giving you insights about the system itself. X are the states, x dot is dx over dt. So what we're modeling here is the change of states with time as a nonlinear function of parameters and inputs. Similarly, we have an output as a nonlinear function. If we do an experiment and measure y hat, we might be interested in looking at the model and making sure that it's close to the experiment, as close to the experiment as possible. So that's the optimization framework, where we might write an optimization problem such as this, where we are optimizing to find out the optimal parameter values. And so that would be the argmin of the error that we want to minimize. So clearly, here we are finding that optimal value. So that's the advantage with this method, that it's we can prove whether the parameter that we find is optimal or not. And the second advantage is that for convex functions, this process can be very efficient. However, there's a couple disadvantages to this method as well. And the first disadvantage is that this is not generalizable. So if you have general nonlinear functions, you may be running into inefficient algorithms for the optimization. And secondly, the important disadvantage is that the uncertainty models are not straightforward. So what do I mean by that? So uncertainty in the data is quite common. Any system working in real environments will exhibit noise and uncertainty. But those are not undesired behaviors, because those will always be the same whenever system response is measured. So our parameters should reflect that ideally, and not just be one value, because that one value is a representative of that particular experiment. So we want to find out how uncertain the parameter values are, and that's not straightforward with this method. So let's move on to the second one. And the second method is the umbrella of learning methods, where you have an input u to the system and output y, and you use that data to find out the mathematical model. So here you don't have the first principles model, and this is very useful in applications where it's not straightforward to create that first principles model, so that you can just use that data to create a neural network or train the weights of the neural network using the data. There's also a couple disadvantages to this method. Because we're not using a first principles model, it is not straightforward to find out physical insights from the trained neural network model. And the second disadvantage is that lots of data is needed to train these models. So, for example, for biological systems, this is not always possible, and so these methods might not be applicable. The third method that we want to that I have here is the probabilistic methods, where instead of finding out the optimal parameter value, we find out a distribution, a probability distribution for each parameter. So for theta, we find out the probability of theta given the data. So here, each parameter value for each one, we know how likely it is. So it's not just one unique value like with the optimization case. So that's the big advantage with probabilistic methods, that we have the uncertainty is modeled. And the second advantage is that we can get physical insights. Also, a couple disadvantages to this method. So one is that it is computationally expensive. Second disadvantage is that the convergence or the optimality is not always obvious. And it's only provably optimal distribution under various assumptions, as we will see later on, because probabilistic methods is the focus of this lecture. So let's look at Bayesian inference. It's one kind of probabilistic method. And Bayesian inference, as we saw earlier, can be stated as sampling from a probability distribution. So we actually just want to find out this probability distribution, P of theta given Y. What's the probability of the parameters given the data? So we want to sample from this probability distribution. If we can do that, then we essentially solve the inference problem. And so to look at how we can solve that, let's take a very simple example and let's think about something slightly different, but very relevant. So if you have a one-dimensional Gaussian random variable, as shown here, and you even know the probability distribution, because we know the probability distribution for a Gaussian random variable, which is written here as mu is the mean, sigma is the standard deviation. So we have this. Now, the problem is, if I ask you, generate n representative samples from Px. So if I ask you to computationally give me an array that has n elements, S1, S2 to Sn, and these should represent a Gaussian probability distribution. So if you want to think about how you could solve this, you can pause this video and think about the solutions to this method. So one obvious way in which we can address this problem is by something that's called rejection sampling. And you can also think of this as random sampling. So what we do essentially here is that we propose sample S. The second step is to draw a random variable u from a uniform distribution from 0 to m. So m would be our maximum value of the probability distribution. So we know what that is for our case. So we sample a value from 0 to m. And the third step is to check whether P of S, so what is P of S? So if, let's say we sample this value, right? In the first step, propose S, let's say we have this value. So that is P of S. And we can compute this because we know what the probability distribution is. So if P of S, so if U, the sample that we get from 0 to m uniform sampling, so that's the random sampling happening over here. So if U is less than or equal to PS, then accept S. So essentially S1 becomes S. If U is greater than or equal greater than PS, then we reject it. And what happens when we reject? Go to step 1. So you basically just keep on going and keep on doing this process repeatedly. And this is very easily possible to do in a Python program. So you can think about that, how you would implement this computationally, right? Because all you would do is just keep on sampling random numbers and then checking if it is less, greater than, or less than this sample here, and then accept the current sample or continue on. So what you can see from this approach is that it's not very efficient. And that is indeed the case. This suffers from curse of dimensionality. So if I increase the dimension of the problem earlier from one-dimensional Gaussian random variable to a five-dimensional Gaussian random variable, then you immediately have to sample 5 values every time at each step, and that becomes computationally inefficient the more dimensions there are. So there are smarter ways of doing it. We won't be going into the details of those, but we'll touch upon those later on. But for now, suffice to say that that we can sample from probability distribution that we know what it is. So two important things are going on here. One is, what if P of X is unknown? And the second thing is how to sample efficiently. So for the first problem that we wrote down above, that is, if the probability distribution Px is not known, which is the common case, we have Bayes' rule at our disposal. And that is the crux of Bayesian inference. So let's think about Bayesian inference problem for 1 second again. What we want is we want to find out the probability distribution for each parameter theta given the data, right? So that's the probability distribution on the left-hand side. It's called the posterior probability distribution. This is what we want to find out. Bayes' rule allows us to write it in a form that is computable, which is the right-hand side. So let's break down each term on the right-hand side. The first term is the probability of data given theta. So this is called the likelihood probability distribution, and you can think of this as a probability of how likely the data is given the parameter values. So if you know the parameter value, if you know what the hypothesis is, you can test that, you can run that simulation of the model, and then depending on how far the model is from the data, gives you a measure on that probability. So let's take a very simple example. If I give you a parameter value, let's say, of a system which has its optimal value at certain value theta, which is 10. And if I give you a sample, which is -2, the model simulation would be very far away from the data. So let's say at 10, the data that we measure y is whatever, 2. So that's the data. But at the given value of the parameter, -2, the model may output 0. And so the model is very far away from the data, and this would imply lower probability of data being likely to be the correct one given this parameter value. However, if I give a parameter value close to 10, I might get some value close to the data, and in that case, the probability that this data is likely is higher. So that is why this is called the likelihood distribution. Similarly, we have the second important part of this equation, which is the probability of theta. This is called the prior probability distribution because it encodes the prior information that we have about the parameters. So again, in our example, if we have a parameter which is optimal at 10, if I know that this is a physical parameter, it models a physical quantity, it cannot be negative, then I can encode that information here by giving a prior probability distribution, which is something like this. I can say something like this, that this parameter is always greater than 5. Then the prior probability distribution for a given value of -2 would reject this because that probability will be 0, so that all values below 5 will be rejected. So that's how we use these two probability distributions practically, the likelihood and the prior. The third term is often called the generative probability distribution. It's the joint probability between the data and the theta. It can be computed by integrating over all parameter values, but it's not easy to compute. The good thing is that we don't really need it. Why is that? because if you think about the Bayesian inference problem, you have the x-axis, which is what you care about. You have the parameter values on the x-axis. And all you need to know is how likely each of those parameter values are. So you may have a probability distribution such as this. And in an ideal case, you would have the probabilities on the y-axis. But if you don't have that normalizing factor, you wouldn't have probabilities on the y-axis, but you would just have other numbers. But the relative scale of how likely each of these values are would still remain the same. And so what we can write is that the posterior probability distribution is proportional to the likelihood times the prior. And taking log of both sides, we can write this in a simpler way, which is that the log of the posterior is proportional to the log of the likelihood plus the log of prior. Now let's take an example to demonstrate how we can compute the log likelihood. The log prior is pretty straightforward because it encodes our prior information. So p theta is something that we write by ourselves. It could be whatever information we know about the parameters. The maximum likelihood can be written as theta ml star is equal to the argmax of the likelihood probability distribution data given theta. And let us consider that we have a discrete example where we have f of theta I plus epsilon I. This is our model where f is not known, and epsilon I is the noise, which we talked about earlier. This is the advantage with Bayesian inference because we can model the effect of the noise in the parameter probability distributions that we get out of it. And these noise are identical and independently distributed. So we can write this as argmax of log of probability of yi's given theta. And assuming that all the parameters are independently affecting the data, we can write this as the product over all parameter values of the probabilities of theta I. So now let's think about this for a moment before writing this as, because log of the products will become a summation of logs of the probability of yi given theta I for all theta I. So now what we have is log of probability of yi given theta I, and this is when we know what the parameter values are. So given the parameter values, what is the probability that yi is the correct data? So now let's go back to the model that we have. Given the parameter value, we can further simplify this, right? Argmax summation over all theta I log of probability of f theta I plus epsilon I given theta I. Now, since the parameter value is given to us, this does not matter anymore, and this probability will be exactly equal to the normal distribution that we know for the epsilon I, the noise. So we have argmax over and since we have log, I'm going to simplify this a little bit by writing log of 1 over 2 pi sigma squared e to the power of minus, what is epsilon I? Yi minus f theta I squared divided by sigma squared. That's the probability of epsilon I, and that's how we can write this. And this will still be summed over all theta I. And finally, since again this is argmax, we have The constant factors don't matter because all we are interested in is the argument of the maximum of this. So we can write this as the negative. So -1/2 argmax. And so we have log and e get canceled. We have minus half yi minus f theta I squared and summed over all theta I values. So we finally have argmax summed over all theta I values. Actually, observe that the negative in the max can be written as min. So argmin summed over all theta I values, yi minus f theta I squared. And this is exactly equal to minimizing the squared sum of errors. Squared errors. Minimizing the sum of squared errors. And this is very important, and it's a fundamental result, and it proves that Bayesian inference can work and can give us the optimal parameter values. Because under these assumptions, under the assumption of IID normally distributed noise, what we find out is actually that the maximum likelihood directly corresponds to minimizing the error. And this is a fundamental concept that goes back to linear regression, optimization, and proves why Bayesian inference can work. Although we clearly see that this kind of theoretical proof would not be possible if we didn't have these assumptions. So that's an important thing to keep in mind. And we can still use it, as I demonstrated earlier, because we have this proof. And if I go back now to the disadvantage that I wrote down for the Bayesian inference, I did say earlier that convergence or optimality is not obvious. And so that's what I meant there. It is only obvious under the condition that we have these nice distributions for the noise. Nevertheless, we can still apply this method, but the convergence would then be much more empirical, and we would have to judge whether the algorithm has converged or not by using empirical measurements and not by mathematical proofs. So that's the crux of Bayesian inference, which we can use. And for general models where even when the noise is not Gaussian like this, we can still minimize the sum of errors. But as I said, the convergence will not be guaranteed. And to address the second point, to conclude this lecture, we have the first problem that we had was, what if the probability distribution is unknown? And we have looked at how to do that using Bayes' rule, and by proving how Bayes' rule lets us write the Bayesian inference problem in a way that is computable, log likelihood and log prior. The second problem was how to sample efficiently, and that is the topic of another lecture. But just to go into it quickly, Monte Carlo sampling is what we did earlier, which was the random sampling, but we can do it smartly. That's called the Markov chain Monte Carlo sampling, or MCMC. I won't go into the theoretical details of this, but suffice to say that what it does is it creates a Markov chain, and it looks at how the previous sample performed in order to propose the next sample. So it does the same proposal and acceptance thing, but much more smartly than just the rejection sampling that we talked about. So we talked about the rejection sampling over here, right? And where we were proposing, and then we were accepting or rejecting. But now with MCMC and various algorithms for Markov chain Monte Carlo, we have the same thing, but smartly done, because it's a Markov chain and it can use the previous iteration and tell you whether to accept the current proposed sample or not. So not going into the details of that, but that can be used to efficiently run Bayesian inference, where what we then do is, if you look at this figure, where we have parameter values on the y-axis, and you have number of steps. So at each step, you propose a parameter value, and then you keep on proposing different parameter values, and the algorithm tries to propose more and more values near the point where it's getting less cost, so where the error is low. And that is how we can lead to a representative sample. So for example, in this figure, we would start with this value, right? And then it's proposing different values, and every time, so for example, when it proposed this value, it may have seen that the cost got increased, so it went down, and then kept on proposing other values. And similarly here, it tried to propose a value over here, but did not propose any other values here because the cost function would be very high. So in the end, if we run this for long enough, what we would find is everything would be sampled near this area, and that would imply that the algorithm is converged, and then we can sample, and then we can take a representative sample out of those values. So that's how Markov chain Monte Carlo implements Bayesian inference. And we can do this with computational tools very easily without even knowing the intricacies of the sampling algorithm. An example is shown here, where you can use Python tools. A package called MC can do this. So for example, all you need to do is create the log prior function. The log prior informs about what you know about the parameter value. So you know something about that M should lie within certain range, B should lie within certain range, M and B are the parameters. And then you create the log likelihood. So that's the sum of the errors squared. That's exactly what we wrote down above. And then we can write down log probability as sum of the log prior and the log likelihood. And then we can use this in sampler, which is the Markov chain Monte Carlo sampler, MCMC, to solve this problem. So we can do this computationally, and that leads us to identification of the parameter distributions. So that concludes the lecture. Hopefully you learned the basics of Bayesian inference and how it stems from the Bayes rule. That's the crux of the whole lecture. And most importantly, how to compute the log likelihood. And that's the proof for how log likelihood can be used to solve the parameter inference problem. Thank you.